Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss a very important topic. Let me write measuring the space time coordinates of an event. So we underline it. So our topic is measuring the space-time coordinates of an event. Remember, in the last lecture, we discussed Lorenz transformation equations. I will list them. Lorenz transformation equations. We have x prime is equal to gamma times x minus ut. Y prime is y. Z prime is z. And t prime is equal to gamma times t minus ux by c square. Right? These are Lorentz transformation equations. We also discussed in the last lecture inverse transformation equations. Then we discuss interval transformation equations and inverse interval transformation equations. The basic idea was this. I'm just refreshing your memory so that I can continue. We have two observers. One is observer S. Second is observer S prime. Let me make the figure first. X prime, Y prime, Z prime. So one observer is S, second observer is S prime. Now they observe some event. We have discussed it already. There is some event and they observe it. This is one observer and we have second observer. Now both these observers observe an event, same event, right? Now according to observer S, the coordinates of the event are x, y, z and t. And according to observer S prime, The coordinates of the same event are x prime, y prime, z prime, and t prime, right? And observer S prime moves relative to S with velocity u. This coordinate system is in motion with velocity u along the common x prime direction, right? So keep this in mind in our discussion. Now, Lorenz transformation equation, which we have listed here, gives us the coordinates of the event as measured by S prime in terms of the coordinates of the event measured by S, observer. Here gamma is called Lorenz vector, and it is equal to 1 over under root 1 minus u square by c square, right? We call it Lorenz factor, right? So let us continue now. Today, we want to first discuss the important question. Let me write how observers S and S prime go about measuring the coordinates x, y, z, t and x prime, y prime, z prime, t prime of an event. So this is our topic. How these observers go about measuring the coordinates of the event. We want to discuss the procedure. And the procedure we now describe forms a conceptual foundation on which actual laboratory procedures can be based. So listen carefully how these observers measure the coordinates. So what we do, we assume that S, observer S, has a large team of assistants available to help in the setting up of a coordinate system. Each assistant is given a clock and a measuring rod of a certain length. I repeat, each assistant is given a clock and a measuring rod of a certain length. For example, three assistants have measuring rods 1 meter in length, right? They are instructed to lay out their rods each along one of the three coordinate axes and to wait at the position determined by the end of the rod until they see a flash of light at the origin, at which time they are to start their clocks at the preset reading of 3.33 nanosecond. What is this time? 3.33 nanosecond. It is the time necessary for light to travel the distance of 1 meter from the origin to the assistant's location. I repeat, let me make a rough sketch. We are talking about observer S. So this is X, this is Y, this is Z. Sorry, this is Z. Let me clear it. This is our X, this is our Y, this is our Z. Now we are talking about the example. We said that this observer S has three assistants and they have measuring rods 1 meter in length. Now what they do, they are instructed to lay out their rods each along one of the three coordinate axes. So let me use this color. Let this be 1 meter rod with assistant 1. So that assistant lays it on x-axis and sits at the end of this rod. So let there be some cartoon. Make it clear. There is some cartoon here, right? And another, so it is its 1 meter rod. Let me use another color. Another assistant lays his rod on y-axis and sits on the end here. And we have another assistant who lays his 1 meter rod on the z-axis like this and sits at the end, right? So they are instructed by the observer S to wait at the position determined by the end of the rod until they see a flash of light at the origin. This is origin. At which time they are to start their clocks at the preset reading of 3.3 nanosecond. That means this green observer has its clock. This red observer has its own clock. This the color is blue. This blue observer has its own clock, right? So what they do, they are instructed by this observer S that they preset this clock at it will have some dial. It will have some dial. It will have some dial, and dial should read 3.3 nanosecond, 3.3 nanosecond, 3.3 nano, 3.33 nanosecond. Let me correct it to be precise. It is, I will use another color. So this dial will read 3.33 nanosecond. This will read 3.33 nanosecond. This will also read 3.33 nanosecond. What is this time? It is the time, but these clocks are at, they are stopped, right? They are not working. I mean to say, observer as instructs them to preset them at this particular value, their dial, and stop them and wait. Wait for what? Wait for the flash of light at the origin. Now, when they see the flash of light at the origin, they are instructed to start their clocks. I repeat, the assistants are instructed to lay out their rods, each along one of the three coordinate axes, and to wait at the position determined by the end of the rod until they see a flash of light at the origin, at which time they are to start their clocks at the preset reading of 3.3 nanosecond. Now, I have already said this 3.3 nanosecond is a time necessary for light to travel the distance of 1 meter from the origin to the assistant's location. So when these assistants see the flash of light, they start their clocks, where dial is already preset at 3.3 nanosecond. There will be three other assistants who are similarly each assigned one of the coordinate axes. They are given rods of length 2 meter and are instructed to start the clocks when they see the flash of light at the preset time of 6.67 nanosecond. I can show, it will become a mess. So at 2 meter, let me use some color. There will be another assistant here. His rod will be of 2 meter length. I will show one of them. It will have its own clock. He is instructed to preset the dial at 6.6 nanosecond. And this particular assistant will start his clock when he sees flash of light at the origin. Now, what is the 6.6 7 nanosecond? It is the time required for the light to travel 2 meters from the origin to the location of the assistant. Now, how you can calculate it is simple. Speed is equal to distance or time Time required to travel some distance is distance or speed. Now if you take distance as 1 meter and speed of light is 3 into 10 raised by 8 meter per second. If you divide 1 meter distance by 3 into 10 raised by 8 meter per second, you will get this value 3.3 nanosecond. If you divide 2 meter distance by this speed of light, you will get 6.67 nanosecond, right? So in general, I can say each assistant is sent to a post, sent to a post with a rod of some length, L, and a clock preset at t equals L by c, where c is the speed of light. Now, when all the assistants are at their posts, observer S sets off a flash of light at the origin and simultaneously starts the clock at the origin, which is preset to 0. I repeat, when all the assistants are at their posts, observer S sets off a flash of light at the origin and simultaneously starts the clock at the origin, which is preset to 0. As the light signal reaches the other clocks, each is started in turn at the preset reading. Thus, the clock on the x-axis at x is equal to 1 meter is started at the preset reading of 3.33 nanosecond when the clock at the origin reads 3.33 nanosecond. The clock on the x-axis at x is equal to 2 meter starts at the preset reading of 6.67 nanosecond when the clock at the origin and the clock at x is equal to 1 meter both read 6.67 nanosecond, and so on for all the clocks in the coordinate system. All clocks in the entire system are thus perfectly synchronized. Suppose that observer S wishes to chart the progress of a particle as it moves through the coordinate system. All that S and the assistants must do is watch the particle as it travels and write down as it passes each point the coordinate and the reading on the clock at that coordinate. Very important. Of course, this calibration holds only for observer S. Observer S prime and all other inertial observers must carry out a similar procedure to define a coordinate system and synchronize its clocks. Right? Now, with such a scheme, the measuring rods and clocks of each observer, which of course are at rest in the frame of that observer, are unique to that inertial frame and are independent of the rods and clocks of observers in other inertial frames. I should write it. It is important. With such a scheme, the measuring rods and clocks of each observer, which of course are at rest in the frame of that observer, are unique to that inertial frame. That inertial frame and are independent of the rods and clocks of observers in other inertial frames. This procedure suggests that space and time are not independent coordinates, but that the description of an event must include its coordinates in both space and time. That is, we cannot use a clock at one location to record the passage of a particle through another location. For this reason, spatial relativity usually is formulated in terms of the combined space-time coordinates x, y, z, and t. Space and time are treated as equivalent coordinates in spatial relativity, right? I hope you got the idea of measuring the space-time coordinates of an event and how the clocks are synchronized. Let us move to next topic. Our next topic is the transformation of velocities. Now, what we are going to do under this heading, we are going to use Lorentz transformation to relate the velocity v. What is v? It is the, let me write, velocity of a particle measured by an observer in the S frame to the velocity v prime of the same particle. Is the velocity of the same particle measured by an observer in the S prime frame, who is in turn moving with velocity u relative to S. We have already discussed that at the start of the lecture. So observer S prime is moving with velocity u relative to observer S. Now our goal is to relate the velocity of the particle measured by an observer in the S frame to the velocity v prime of the same particle measured by an observer in the S prime frame. Now to do this, we'll make use of Lorenz transformation, right? So let us move forward. Suppose observer S finds the particle to move from coordinates x1, y1, z1, t1 to x2, y2, z2, t2, right? Observer S prime, on the other hand, records the observations of the initial and final coordinates of the same particle as x1 prime, y1 prime, z1 prime, and t1 prime, and x2 prime, y2 prime, z2 prime, and t2 prime. So prime coordinates are relative to S prime observer, and without prime coordinates are relative to observer S. Now let us calculate Vx prime, which is delta x prime by delta t prime. What is it? It is x prime component of the velocity measured by S prime. This x prime component of the velocity of the particle measured by S prime. So we can calculate it. We have to simply use the Lorenz equation. Let me use here another color. So Vx prime will be therefore, what is delta x prime? It's gamma times delta x minus u delta t, and delta t prime is gamma times delta t minus u delta x by c square. Remember the Lorenz transformation equations. X prime is gamma times x minus ut. So delta x prime is therefore gamma times delta x minus u delta t, and delta t prime is gamma times delta t minus u delta x by c square, right? So we have simply used the interval transformation. So we are here. So we obtained Vx prime equal to gamma times delta x minus u delta t over gamma times delta t minus u delta x by c square. So gamma cancels out. What we get, we can write it this way. We can write it delta x by delta t minus u over 1 minus u times delta x by delta t over c square. Chuck it. Gamma times delta x minus u delta t over gamma times delta t minus u delta x by c square. Then we simplify it and write delta x by t delta t minus u over 1 minus u times delta x by delta t over c square, or replacing delta x by delta t by Vx. What is Vx? It is the x component of the velocity of the particle as measured by observer S. So when we do it, what we get Vx prime is equal to Vx minus u over 1 minus u Vx by c square. Let me encircle it. We name it first. What is Vx prime? It's x prime coordinate of the velocity of the particle observed by S prime observer. Vx is the x component of the velocity of the same particle as measured by observer S. U is the relative velocity of the two observers. C is the speed of light, right? Now, in a similar fashion, we can obtain transformation equations for y and z components of the velocities. So Vy prime will be, chuck it, I will write directly Vy over gamma times 1 minus u Vx by c square, and Vz prime is Vz over gamma times 1 minus u Vx by c square. Let me encircle them. Let me name this second and this one third. Now, how you can obtain it? Simple. Vy prime will be delta y prime over delta t prime. You make the substitution, accordingly set the things, and here Vz prime will be delta z prime over delta t prime. For delta z prime and delta t prime, you will make use of the Lorenz transformation equations in the form of interval. Then you will obtain these equations. To check it at home. This is your assignment. So let us move. Right. So Vy prime is the y prime component of the velocity of the particle as measured by s prime observer. Vy is the y component of the velocity of the same particle as measured by observer s. Gamma is the Lorenz factor. U is the relative velocity of the two frames. C is the speed of light. Similarly, Vz prime is the z prime component of the velocity of the particle as measured by s prime observer. Vz is the z component of the velocity of the same particle measured by observer s. Gamma is the Lorenz factor. U is the relative velocity of the two frames. Right. Note that Vy prime is not equal to Vy, even though delta y is equal to delta y prime. Let me show you the Lorenz equations. So y prime is y, delta y prime will be delta y. Same goes for the coordinate z. But still, Vy prime is not equal to Vy. Reason is delta t is not equal to delta t prime. Similarly, Vz prime is not equal to Vz, even though delta z and delta z prime are equal, because delta t is not equal to delta t prime. Right? This is another example of the difference between the way the Galilean and Lorenz transformations deal with the time coordinate. Right? Be sure to note that the denominators of all the three equations include the factor Vx. You can see in this denominator you have factor Vx, and in other two equations there is also a factor of Vx. Right? Now these equations 1, 2, and 3. Let me use another color. Now equations 1, 2, and 3, they are called Lorenz velocity transformation equations. They are analogous to the equations of the Lorenz coordinate transformation. They relate observations in one coordinate frame to observations in another. Right? I can summarize them this way. I will write the Lorenz velocity transformation. On one side, I will write velocity transformation. On another side, I will write inverse velocity transformation. Now, velocity transformation we have obtained. Vx prime is Vx minus u over 1 minus u Vx by c square. Vy prime is Vy over gamma times 1 minus u Vx by c square. And we have, let me change the, let me use the same. Vz prime is Vz over gamma times 1 minus u Vx by c square. And in inverse case, let me use this color. Vx is Vx prime plus u by 1 plus u Vx prime by c square. Vy is Vy prime over gamma times 1 plus u Vx prime by c square. Vz is Vz prime over gamma times 1 plus u Vx prime by let me rewrite it here. There is no space. Write it here. Vz is Vz prime over gamma times 1 plus u Vx prime by c square. Let me check them. Vx is Vx prime plus u over 1 plus u Vx prime by c square. Vy is Vy prime over gamma times 1 plus u Vx prime by c square. And Vz is Vz prime over gamma times 1 plus u Vx prime over c square. I've already discussed in case of Lorenz coordinate transformation equations how to obtain inverse transformation from the simple transformation. You simply do what? You can obtain inverse transformation from these transformations. We replace u by minus u and we exchange the primed coordinates with the unprimed coordinates. For example, here we have Vx prime, we write instead Vx, and this unprimed we change to primed, we write instead of Vx, Vx prime. we replace u by minus u, so it becomes plus. Same goes here, it becomes plus, and vx is replaced by x prime, prime coordinate. Same goes for other equations, right? So this is all for today. I will give you a question. Question is, let me write it. Homework. This is the question. Observer S reports that an event occurred on the x-axis at x is equal to 3.2 into 10 raised power 8 meter at a time t equals 2.5 second. Part A, use another color. Observer S prime is moving in the direction of increasing x at a speed of 0.38 c. What coordinates is the speed of light? You know that. What coordinates would S prime observer report for the event? Now part B. What coordinates would S double prime observer report if S double prime observer were moving in the direction of decreasing x at this same speed. I will repeat the question. Observer S reports that an event occurred on the x-axis at x equals 3.2 into 10 raised to 8 meter at a time t equals 2.5 seconds. Part A, observer S prime is moving in the direction of increasing x at a speed of 0.38 c, where c is the speed of light in vacuum. What coordinates would S prime observer report for the event? Part B, what coordinates would S double prime, another observer, report if S double prime were moving in the direction of decreasing x at this same speed? So here, in case of S prime observer, the observer is moving in the direction of increasing x. S double prime observer is moving in the direction of decreasing x. So this is your homework. Do your homework. And I repeat, the first topic was a bit thought-provoking, measuring the space-time coordinates of an event. You give it a thought. It's very important. You can understand it. No worries. Follow all the video lectures keenly and patiently. Don't waste your time. And don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.